Welcome to the Explainer. Today, we are diving deep into the architecture of high-performance C++, looking at the patterns that drive some of the absolute fastest systems in the world. So let's kick things off with a pretty provocative question. Why do systems where every nanosecond counts, think high-frequency trading or AAA game engines, so often ditch virtual functions, which are, the bedrock of object-oriented C++? And let's be clear. We're not talking about small, nitpicky optimizations here. As this quote lays out, these are massive architectural decisions. Getting them wrong doesn't just slow you down. It can lead to systems that fail, and fail catastrophically when you try to scale them. So here's our game plan. We'll start by defining the problem. Then we'll put some real numbers on the performance hit. After that, we'll explore the solution that happens at compile time, look at the specific patterns that get us there, face the trade-offs, and wrap it all up with a clear architectural mandate. Okay, let's get right into it. We're going to start with a classic problem in object-oriented design, one that starts as a small inconvenience but can quietly grow into a full-on architectural nightmare. It's called the fragile base class problem, and it's a real headache. This is where you make what seems like a totally safe internal change to a base class, and suddenly, completely unrelated derived classes start breaking in weird and wonderful ways. Maybe they get stuck in an infinite loop or just start producing wrong answers. And this isn't just some academic thought experiment. This problem creates very real technical debt. Your code becomes brittle, it gets harder and harder for new engineers to get up to speed, and your development cycle slows to a crawl because everyone is afraid to touch anything. So we have this architectural fragility, but it gets worse. That same feature, the virtual function, also comes with a serious, measurable performance hit. Let's put some cold, hard numbers on the cost of using virtual. So the magic behind virtual is something called dynamic dispatch. Basically, when your program is running, it has to stop and look up the right function to call in a special list called a virtual table, or vtable. This gives you that awesome runtime flexibility, but that lookup, it's not free. So how not free are we talking? Well, benchmarks show it can be around 20 times slower than a regular function call that the compiler can just inline directly. You're looking at a jump from under a single nanosecond to 13 nanoseconds or even more for one single call. And what's really fascinating here is the why. This table breaks it down beautifully. The virtual call completely blocks the compiler's number one optimization, inlining. Just look at that row. It goes from guaranteed to blocked. Then there's the cache cost from having to go look at that vtable. But the real killer is that last row, branch predictability. And that last point is absolutely crucial. A virtual call is what's called an indirect branch, and modern CPUs are just terrible at guessing where they're going to go. When the CPU guesses wrong, it has to throw out everything it was working on, a penalty of 10 to 20 clock cycles. In the world of high-frequency trading, that kind of unpredictable latency, that jitter, is a complete disaster. So if making these decisions at runtime is causing all this pain, what's the solution? Well, it's pretty straightforward, actually. You stop making decisions at runtime. You shift all of that work to compile time. And this slide really gets to the heart of the philosophical shift. We're moving away from flexible but slow runtime strategies and toward compile time policies. These behaviors get baked right into the executable, giving you maximum performance with zero overhead. And the tool that lets us do this is static polymorphism. It's a fancy term, but the idea is simple. We use C++ templates to let the compiler figure everything out and wire it all together before the program even runs. This completely gets rid of the need for vtables and dynamic dispatch. Okay, theory is great, but how do we actually do this? Let's dive into two incredibly powerful C++ patterns that make this compile time philosophy a reality: policy-based design and the curiously recurring template pattern. So first up is policy-based design, or PBD. The best way to think about this is like building with Legos. You have your main class, which is like a base plate, and then you just snap on different policy classes as template arguments to give it different behaviors, maybe one for thread safety, another for logging, you name it. This code snippet says it all, doesn't it? On the left, the old way, you need a pointer to an interface, and every call to lock is a costly virtual call. But on the right, with the policy-based version, the compiler just stamps out the code. That call to lock becomes a direct, static function call that will absolutely be inlined. The runtime cost, 0. All right, next up is a pattern with a famously weird name, the curiously recurring template pattern, or CRTP. Now, don't let the name intimidate you. It is a really clever trick for getting all the benefits of inheritance without any of the vtable overhead. So here's the magic behind it. First, your base class is a template. Then, and this is the curiously recurring part, the derived class inherits from the base and passes itself as the template argument. Because of this, the base class now knows the exact type of its child class at compile time. So for step 3, it can just use a static cast to call the derived methods directly. No vtable, no lookup, no overhead. It's brilliant. Okay, so this all sounds amazing, right? Zero cost abstractions, incredible speed, it feels like a free lunch. But you know there's a catch. And with these patterns, the catches are significant and you absolutely have to understand them. First, with policy-based design, you can run into something called a combinatorial explosion. That awesome flexibility at compile time means that if you have, say, a class with 4 different policies, and each policy has 3 different implementations, you've just told the compiler to generate 81 unique versions of that class. Your binary size can balloon, and your compile times can just grind to a halt. But the biggest drawback, the absolute deal breaker that dictates where you can and cannot use these patterns, all comes down to 3 letters. ABI, the application binary interface. Here's the problem. Because all this template magic has to live inside a header file, any change to its internal structure, adding a private member, changing a type, breaks binary compatibility. That means every single part of your project that uses that header has to be recompiled from scratch. This makes static polymorphism completely unusable for public APIs, for plugin architectures, or for shared libraries that you want to update independently. And that brings us to the final and most important takeaway. This isn't about static polymorphism being good and dynamic being bad. It's about being a smart architect and deliberately choosing the right tool for the right job. This table is really your cheat sheet. Static polymorphism gives you jaw-dropping performance, but you pay for it with compile time complexity and a totally unstable ABI. Dynamic polymorphism gives you that stable ABI and runtime flexibility, but you pay for it with performance overhead and the risk of a fragile base class. So the mandate is clear. Use static patterns for the performance-critical internal core of your system, but for your public, stable API boundaries, you stick with dynamic polymorphism. So the next time you're starting a project, ask yourself this simple question. What's the more expensive problem for me to have, unpredictable runtime latency, or the headache of maintaining long-term ABI stability? By making that choice consciously, you're not just writing fast code, you're engineering a system that's robust, maintainable, and truly built to scale.